All right, so this is a review of homework 3, which is an introduction to proof in propositional logic. Proof in propositional logic is sometimes called the propositional calculus, which is just a general use of the term calculus. It doesn't relate to calculus in math. And its more traditional name is actually natural deduction. If you're interested, natural deduction has kind of an interesting etymology. You could look it up in Wikipedia. But it's basically to distinguish this way of doing proofs from a very spare axiomatic system, which was sort of derived from other axiomatic systems like Euclidean geometry, and most people found extremely difficult and tedious to work with. So the systems that we learn today are actually meant to be a lot more natural, a lot more like reasoning in natural languages, even if our initial introduction to them, we don't experience them that way. So it's important to understand that natural deduction, or the propositional calculus, is something very different than trees. Trees are really a fully algorithmic method of determining whether arguments are valid or invalid. That's to say that it's completely mechanical and it's fully effective in determining the answer. Natural deduction isn't like this at all. It requires thought, it often requires creativity, and it is in no way guaranteed to give you the right answer. Well, that's a little bit of an exaggeration, because the propositional calculus that we're learning here can actually be made into an algorithm, but following it would be extremely tedious. But right now you might reasonably wonder why, given that we have a tree system that's fully effective, we even bother with some other system that's apparently weaker. And that's actually a really good question. If all we ever did was propositional logic, natural deduction would be kind of pointless, except just as an interesting exercise. But the problem is, and this is something that was discovered early in the 20th century and really ranks as one of the great discoveries of logic, is that when we develop systems of greater and greater power, it's impossible to develop trees with the same kind of, or tree systems with the same kind of effectiveness as we have in propositional logic. So in those cases, all we have is proof. If you've taken any advanced mathematics, or even just semi-advanced mathematics, you may have encountered mathematical proofs, and you certainly didn't get tree versions of these proofs. And that's because mathematics is a language that's extremely powerful, much more powerful than the propositional calculus. And we just can't develop tree systems for mathematics. So the reason we learn natural deduction beginning at this level is because it's much easier to learn the basics here. And then when we get into more powerful manifestations of the language, like predicate logic and set theory, this will be quite a bit more familiar to you. Okay, so what we're looking at here is stuff I've gone through in the videos, and of course I'm just going to have to assume that you've acquainted yourself with these. But these are just the basic rules for doing propositional logic. Now by basic here, we don't just mean easy or something. We mean these are the rules that we just adopt primitively without any proof or really even justification. In reality, all of these rules can be represented as tautology in a truth table, and you might say that's why we adopt them at this primitive level. And that really wouldn't be all that wrong. But it also glosses a really important fact that we'll be returning to a lot. And that is that a system of proof is completely different than the semantic system of interpretation that we were developing earlier. So when we develop systems of proof, we definitely want them to align with our semantic systems. And what we mean by that is that what we end up calling theorems in a proof system are things that we want to end up being tautologies or necessary truth in the semantic system. And in fact, we would always consider it a very great failing of a proof system that it's capable of deriving things that aren't tautologies or what we sometimes call validity in the semantic system. Now, if this stuff, what I'm saying in the last couple of minutes, is really just sort of not making a whole lot of sense to you, don't worry about it. It's sort of the philosophy behind all this, and we'll be returning to it quite a bit. For now, we're really just going to focus on the mechanics here. So if you look at these rules, and by the way, this sheet is available to you within the module, you'll see that these rules are often very similar to the tree rules that you've learned, but it's important to realize that they are not those rules. They are different rules. They are rules that apply specifically to the natural deduction or propositional calculus system that we're developing here. Having said that, the first rule, negation elimination, simply allows you to infer P from not P in an analogous way to the tree rule. Conditional elimination does not have a correlate within trees. It allows you to infer from two propositions, if A then B, and A that B. So if P then Q, and if you have if P then Q on a line, and you have P on another line, then you can write Q. And over here, we write a justification. Now this too is very different than the trees. Tree systems are sometimes developed so that you do write justifications on the right-hand side, but they really get messy and tedious, and we tend to avoid that sort of thing when we're doing trees. But when we're doing proofs, you absolutely have to cite your justification. So when you do execute a rule, you always cite the justification of that rule. And it's very important to be aware of when in that rule, how many lines are actually involved in the justification. So with conditional elimination, which by the way is sometimes called modus ponens, that's the traditional term for it, there are two lines that have to be cited. Okay. Third rule, conjunction introduction, just allows you to put two different lines together with a conjunction. So if you have P on one line and Q on another, you can write P and Q by 1, 2, and introduction, or conjunction introduction. Now, of course, this doesn't have to be just a P and a Q, right? They don't have to be atomic propositions. They can be any propositions whatsoever. Conjunction elimination is sort of the reverse process. Here you only need to cite one line, but it tells you that if you have a conjunction on one line, then you can cite one or the other of the conjuncts on a subsequent line, just citing the original conjunction and conjunction elimination, the rule of conjunction elimination. You'll notice that both with conjunction introduction and conjunction elimination, there's two different formulations, and you'll see that below too, which just allows you or reminds you that you can do these in different orders. Okay, and then we have 4 more rules. We have disjunction introduction. Disjunction introduction is a funny rule intuitively. It tells you that if you have any formula at all on a line, say P, then on some other line you can write P or just anything you like, P or Q. And you could also write Q or P. And the reason for this is simply that a disjunction, and what I mean here, of course, is that the semantic reason for it, the truth table reason for it, is that a disjunction is a proposition that is true if only one of the disjuncts is true, right? This is what you learned from the truth table for disjunction. So if you know P is true, then P or anything else also has to be true. Now, none of these rules are terribly challenging, but disjunction elimination tends to be the most challenging for people. The basic idea here is that if you have a disjunction, P or Q, say, and you know that both disjuncts imply the same thing. So if you know that P or Q, and you know that if P then something, and you know that if Q then something, then you can infer that something, right? So the basic idea here is that when a disjunction is asserted, all we know is that one or the other of the disjuncts is the case. So if we want to infer anything from that disjunction, it has to actually follow from both of the disjuncts. So when we cite disjunction elimination as our rule, we actually have to cite 3 lines. We have to cite the original disjunction, and we have to cite both conditionals. Now later on, by which I mean in the next homework, disjunction elimination is going to be something we exploit a lot. And it's going to be because we'll be given a method for actually constructing the conditionals on line 2 and 3. So I'll leave that for later explanation. So biconditional elimination and biconditional introduction are easy. If you know that something like if P if and only if Q, you can infer if P then Q, and you can also infer if Q then P by one biconditional elimination. This, of course, follows from the definition of the biconditional. A if and only if B just means A if and only if if A then B and if B then A, right? So it's a conjunction, and so we're just exploiting the conjunctive nature of biconditional elimination. And we're also exploiting that with biconditional introduction. So if you know that if P then Q, and if you know that if Q then P, then you're entitled to assert that P if and only if Q by 1-2 biconditional introduction. Okay, so that's a review of the rules and how to use them. So now let's just go straight to the homework. Okay, the homework begins with some hints, and I'm just going to skip those for now and just start. So in the first one, we're supposed to derive, to prove, from 3 premises: P or Q if and only if F, P or Q if and only if S or T if and only if M, that M and P. Okay, so the first thing you do whenever you do a proof is you write down the assumptions and you label them as assumptions. And so our task is to show that if we're permitted to make these 3 assumptions, then it necessarily follows that M and P. In other words, we're going to derive M and P from these 3 assumptions. Now, there's absolutely no way to do this unless you've committed these rules to memory. If you're hoping to just avoid this sort of thing in general, that's a vain hope. You do have to learn these things and get them to become part of your brain. If you don't, you're really going to be in the position of someone who's trying to speak a language but is always looking every single word up in the dictionary. Now the next step, and this is the case with all proof, is that you really want to spend some time what we sometimes call reverse engineering the problem, right? So you're familiar with this way of thinking. If you've done any programming, you basically look at the result you're trying to get, and then you work backwards. So in this case, you see that you're trying to prove a conjunction. Now, when you're trying to prove a conjunction, almost always what you're going to try to do is prove each conjunct, each side of the conjunction, separately. So first, not really first necessarily, because it doesn't matter what order, but you're going to prove M, and then you're going to prove P, and then you're just going to put them together using the rule of conjunction introduction. So your first question would be, how am I going to get P? Or excuse me, how am I going to get M? Well, if you look at the third assumption, you can see that S, if you applied biconditional elimination to line 3, you would have not S or T if and only if M, but you would have if S or T, then M. And that means that you could use conditional elimination if you had S or T to produce M, right? So then you say, well, I wonder if there's any way I could get S or T. Well, if you had S, you could get S or T by disjunction introduction, or if you had T, you could get S or T by disjunction introduction. So you look around and you ask yourself, well, where is one of these? And if you look at line 2, you'll see that there's an S, but you'll note by the same reasoning as before that the only way to get S is, or at least not necessarily the only way because you don't know that yet, but one way to get S would be to get P or Q, right? Because if you had P or Q, if you applied biconditional elimination to line 2, you'd have if P or Q, then S. And then if you could get if P or Q, you could have S by conditional elimination. So now your whole project turns on, can you get P or Q? And then you have an aha moment. You see, well, I have P right here, so clearly by OR introduction, I can get P or Q. And then basically you've just solved this proof and you just need to reconstruct the steps in the reverse order. Now, there isn't any one specific order you need to do these in. There's a lot of play in this, right? So you could first use OR introduction to create P or Q, or you could first do biconditional elimination to create if P or Q, then S, right? But no matter which order you choose, this is what you're going to end up with, right? So I'm going to write if P or Q, then S by 2, like line 2, biconditional elimination. And then I'm going to write P or Q by line 1 and OR introduction. Like I said, I could have done that in the reverse order. You just need to choose one. And now, do you see what I need to do? You ought to stop and make sure you know what I'm going to do next. Okay, so because I have P or Q and because I have if P or Q, then S, now I'm allowed to write S by line 4 and 5 conditional elimination. Remember that conditional elimination always involves 2 lines. If you ever find yourself writing one line in conditional elimination, you've made an egregious mistake, and it's probably because you're failing to distinguish in your head conditional elimination and conjunction elimination. Conjunction elimination involves 1 line, but conditional elimination involves 2 lines. Very, very important to get that straight. Okay, so if you're following this, you should see what we're going to do next, because it's really the same reasoning that we just applied, only using S now. So now we produce on line 7, if S or T, then M by biconditional elimination again, but this time from line 3. And then we create S or T through disjunction introduction again, but this time on line 6. And this provides us, just as before, with m. So we have m by 7 and 8 and the rule of conditional elimination. But we don't just want m, do we? We want m and p. But what I failed to emphasize when I was doing the reverse engineering, p, of course, is just given to us, right? So now all we have to do is put m and p together by 1 and 9 and conjunction introduction. All right? And so that's our very first propositional calculus proof. You'll see how different it feels from the tree rules. Here, we've actually generated the conclusion we want. We've proved it, we've derived it, we've shown that given the first 3 assumptions, m and p can be derived, which is a way of saying these first 3 assumptions actually, in some very deep sense, contain the conclusion. Now, as I suggested before, this proof system just isn't as powerful as trees. We don't have a way in this system, or at least in proof systems generally, to show that there's no way to derive a conclusion from specific premises. So if we fail to derive a conclusion from a set of premises, there's really nothing much interesting we can conclude. It could be because it's impossible to do so. In other words, that the argument is in semantic terms invalid and we shouldn't be able to prove it. Or it could be just that we're not very good at proving, or it's just very, very difficult and we just didn't succeed in doing so. Okay, so moving on to number 2, I'm going to start to speed things up just a tad. So here we're given 4 assumptions, P and S, P if and only if R, if S then T, and if T then R. And we're being asked to prove a disjunction, right? Now, when I say we're being asked to prove a disjunction, what am I saying? I'm saying that or, the wedge, is the main operator, right? And so that's taking me back to what I've been emphasizing all along, that if you aren't developing the skill of identifying the main operator, you're going to be really compromised in your ability to do these, okay? So when you notice that we're trying to prove a disjunction, then you want to be alive to the possibility that all you're going to do is prove one or the other of the disjuncts and add the rest of it through the rule of disjunction introduction. And so in this case, it looks like the conclusion is this really big, hairy thing that might take a lot of work to produce. But consider the possibility that all you need to do is derive T. If you could derive T, then you could, in one step, get this whole conclusion through disjunction introduction. So ask yourself, is there any way to get T? And it turns out that it's very simple. We have if S then T on line 3, right? And we have S just sitting here in line 1. So if you pull S out through conjunction elimination, apply conditional elimination to the results, you're going to get T very quickly, and then you'll just be able to get your conclusion through disjunction introduction. So what this proof helps you to understand as well is that you're in no way committed to using all of the assumptions. Often it's the case, or maybe even typically it's the case, that you will use all the assumptions, but there is no rule that says that you have to. All right, so this is the proof. Only 3 steps. You get S through line 1 in conjunction elimination, and then you get T by applying 3 and 5 through conditional elimination, and then on line 7, you get your conclusion simply by doing a disjunction introduction on line 6. Okay, on problem number 3, you are given 4 assumptions and you need to derive S from those assumptions. So when you're reverse engineering, you want to go S hunting, right? Well, S only appears right here. When you see that there is a conditional that would generate S, you notice that what you really want now is R, and you also want if R then S on a line by itself so that you could apply conditional elimination. Well, when you look at line 4, you know that double negation, right? Negation elimination would give you your R. So then the question becomes, how do you get if R then S? Well, the way you get if R then S is by somehow getting P if and only if Q. But P if and only if Q is almost right there for you. You just need one rule, namely biconditional introduction, to create P if and only if Q. So again, lots of choices with respect to order, but I can create R through negation elimination on line 4, and then I construct P if and only if Q through 1 and 2 in the rule of biconditional introduction. That gives me the antecedent condition of line 3, right? So now I can just apply conditional elimination to get if R then S, and then I'll also be able to apply conditional elimination to get S. All right? So here, of course, the order does matter because there's no way we could get S before we've got if R then S. So first, you have to apply conditional elimination to lines 3 and 6 to get your conditional if R then S, and then having done that, you can apply conditional elimination again to lines 5 and 7 to get your conclusion S. All right, in this fourth one, you're being asked to prove from only 2 assumptions, but 2 assumptions with a fair amount of content, something whose main operator is a conjunction, and then also whose conjuncts are conjunctions too. So this is a string of conjunctions, and it will probably occur to you, in this case correctly, that you're probably going to have to generate these individually and then put them together by a series of and introduction or conjunction introduction. So if you reverse engineer this problem, you'll see that you've got not T and not R, which you know will give you both T and R on lines by themselves quite easily, and then would allow you to reconstruct this as T and R. Now here's a very important little teaching moment. You might think, well, can I just do something like this? T and R by 2 and conjunction, and negation elimination. So the answer to that is no, and there are 2 reasons. They're both very important, but the most fundamental one, first, is that when you are applying these rules of inference, you always have to be operating on the main operator. So again, this is further proof of the importance of being able to identify the main operator. Just turn that red to make it clear that we're not allowed to do this. So what that means is that you can't operate on not T, and you can't operate on not R until they're on lines by themselves. Now the second and also very important reason is that if you did it this way, you'd actually be applying the rule twice. Once to not T and once to not R, and you can't do that. you can apply a rule only once to one line. Very much later in the course, we'll liberalize things a little in that area, but not now. So your next several steps are going to look like this. Get not t on a line by itself, get not r by a line by itself, apply negation and elimination to each, and then put them together to create the conjunction T and R. And why are you doing that? Because you know that T and R, right, will produce P and M if you apply biconditional elimination to line 1. So the next 4 lines in the proof look like this. If T and R, then P and M by biconditional elimination on line 1. Then you get your P and M because you have 7 and 8 that you can apply conditional elimination to get P and M. And then you just take P and M apart, put them on separate lines. Why are you doing that? Well, because you need them on separate lines to finally build this formula through applications of conjunction introduction. Right? So line 12, put P and T together through conjunction introduction. Line 13, put R and T together through conjunction introduction. And line 14, you create your conclusion by conjoining lines 12 and 13 again through conjunction introduction. Okay, proof number 5, you're being asked to prove a conclusion which has as its main operator what? Right? It's a disjunction. So that strongly suggests that you're going to be using disjunction introduction. And then if you look even a little deeper into this conclusion, you can see that one of the disjuncts is itself a string of disjunctions. So one hypothesis you might formulate here is that really all I need to do is get M, right? Or just get N, right? Because if I did, then I could create M or N, and I could create M or N or K, and then I could create S if and only if P or K or M or N, all through or introduction. That's a good hypothesis. It doesn't quite work exactly that way. That's the kind of insights you want to exploit, even when they're not really completely right. So what you see instead is that we have M or N as the consequent of this conditional, right, on line 2, and you see it on line 3 as well. And so you know that if you could just get P, or if you could just get S, then you would have M or N, and then you could simply build up the conclusion through or introduction. Now, in reality, you can't have P and you can't have S. You're given P or S, and that's it, right? So there is no, so again, a very important don't do this teaching moment. There is no or elimination that lets you write for, say, P1 disjunction elimination. Again, that's in red because you absolutely can't do that. There simply is no rule that allows you to do that. And really, you don't just have to rely on rote memory here, even any more than you have to rely on rote memory to remember that conditional elimination necessarily involves 2 assumptions. This is really how English works. It's natural. Remember, natural deduction. You would never allow yourself to say, or anyone else to say for that matter, for example, if it rains, then I need an umbrella. Therefore, I need an umbrella, right? It doesn't follow from if it rains, then I need an umbrella, that you need an umbrella. It only follows that if it rains, it only follows from if it rains, then I need an umbrella, that when you have the assumption that it rains, you need an umbrella, right? That's why you need the antecedent condition stated on a line by itself. Now in this case, similarly, you would never allow yourself or anyone else to say it's hot or it's cold, therefore it's hot, right? But what you would allow, what you would permit as rational is someone saying, look, it's going to be hot or it's going to be cold. If it's hot, we're having this party. And if it's cold, we're still having this party. So we're going to have this party, right? So that's the nature of disjunction elimination. It's not this, but it is this, right? So because you have P or S, and because you have if P then M or N, and because you have if S then M or N, you now have M or N by 1, 2, 3, and disjunction elimination. And because you now have M or N, you can get K or M or N, and then you can get S if and only if P, or K or M or N. So just 2 more steps. So again, the order here definitely does matter. You couldn't do 6 before 5 because you wouldn't have had 5 to build 6. So K or M or N by 4 in disjunction introduction, and then the conclusion by 5 in disjunction introduction. All right, so number 6, you've got a list of 4 assumptions from which you're asked to derive Q. And now we're at the stage where I can tell you that if you ever have one or more assumptions that are disjunctions, then in order for them to participate usefully in your proof, you are probably going to have to use the rule of disjunction elimination. So the way this, you can see this playing out here, if you do your usual reverse engineering, is you know that you want Q. You'll notice in the second assumption, we have if J then Q, so it would be nice to get J. But the only way you're going to get J is by getting L, at least as far as we've explored. Then you'll notice in the third assumption, you've also got J if and only if Q. But the way to get J if and only if Q out of that would be to first get T and S. Okay, so then you look at your first assumption, your disjunction, and you'll notice that you've got both L and you've got T and S, but in a disjunction, right? So if you've grasped the rule of disjunction elimination, you know that with or after a few applications of biconditional elimination, you will be able to get J if and only if Q through disjunction elimination. So what does that look like? Looks like this. Lines 5 and 6 are both simply applications of biconditional elimination to lines 3 and 2. And then, because line 1 asserts that L or T and S, and we now know that T and S yields J if and only if Q from line 5, and L yields the same from line 6, we can now simply assert J and if and only if Q through the rule of disjunction elimination, which involves the citing of 3 lines. The original disjunction, always write that one first, and then the 2 conditionals that you require. Ordinarily, you'll write the one that comes first in the proof first and the one that comes later in the proof second. So by 1, 5, 6, and disjunction elimination. And now you're just 2 steps from finishing the proof. You get J by negation elimination on 4, and then you get Q by 7 and 8 conditional elimination. Okay, and this last one, number 7, is maybe a tiny bit tricky. If you look at, you've got 5 assumptions. You're being asked to prove a disjunction. So as I've said before, when you're being asked to prove a disjunction, you want to strongly suspect you're going to use disjunction introduction. There's a lot of ways this could occur here. You could get S and add in R and then add in T. You could get R, then add in S and then add in T. You could get R or S and then add in T. Or you get T and then add in R or S. All of those could work. You really don't know until you look what you're going to be able to do. And so really with proofs, you just have to play around. Often you're going to arrive at dead ends and you just need to try something else. So in this case, rather than speculate on which one of these you should get before adding in the others, you might just look at the assumptions. If you look at 1 and 2, you can see that they are both conditionals, and the second one is the transposed version of the first one, which means if you put them together using biconditional introduction, you would get this, the antecedent of the conditional on line 3. So you know that you could produce, if you want, P or M. Now P or M is a disjunction, not very informative. However, if you look at lines 4 and 5, you can see that both of the disjuncts imply the same thing, right? Which is T, and T is one of the atomic propositions from which you can build the entire formula. All right, so how does that work out? On line 6, you put T if and only if R or S. Create T if and only if R or S by lines 1 and 2 and by conditional introduction, and that gives you P or M by lines 3 and 6. Conditional elimination, then you take advantage of line 7, the disjunction, and lines 4 and 5, right, to apply disjunction elimination to get. So on line 8, we have 7. On line 8, we have the original disjunction, 7, and then the 2 conditionals, 4 and 5. The appeal to the rule disjunction elimination to get T. And then finally on line 9, we just add in R or S by 8 in disjunction introduction. So I said that was a little tricky, and although this is very straightforward as I explained it, there's a good chance that when you did it on your own, you thought that R or S is something that we would end up getting on a line by itself and adding T. And that was a good guess, just didn't happen to work out that way. Okay, so that's the end of this review. Let me just finish by saying something a little admonishing. So if you did all the homework and you watched this and sort of saw that with maybe very few errors, what I did is what you did, you're in fantastic shape. But if you didn't do all the homework, or if you did try it but struggled, and then you watched this video and sort of just said, okay, oh yeah, now I see what I did wrong. Oh, now I sort of get it. Okay, great. And concluded that you now understand it. I just got to tell you that you don't. The only reason you're going to have, or good reason you're going to have for thinking you understand these, is if you can reproduce every single one of these proofs on your own without looking at the video. So it's very common to think that there's no point in doing that since you just saw the proof. But there is a very important point in doing that, and that is that very rarely are you ever going to be able to replicate any of these proofs by memory. So what you need to do each time when I finish a proof is stop and then do it on your own. And if you can't do it on your own, then you got to go back and figure out why. Okay, so this is really the advantage to having these videos, is that you can stop me, rewind me, replay me as many times as you want without ever worrying that you're boring your fellow students or taking up too much valuable class time. But you got to do it. You got to be really aggressive in using the videos in this way. If you do, the online class can be a revelation to you in terms of just how much better you can do. But if you don't, then this online format just becomes your undoing. Okay, that's it.